All right, line V2, learning task 2, we're going to take a look at AC controls maintenance. And basically, it's going to be a lot of a reiteration of what we saw in the first one there, where we're going through kind of the charts and, what we might have for problems on different types. This one's going to be much more laid out about how we go and apply testing that we are going to go and have. And it's going to be based around the assumption that we have got a motor that is not operating for whatever reason. If the motor is not operating, we're going to go and work our way through a control system, starting with where we know we should be good, working our way all the way back down to where we know that something has gone badly. So over here we've got bad, over here we've got good. We know that whatever happens, we should always have good power that's going to be applied on my lines. So I can start working from there all the way back through. I'm going to use a couple of different things to do so. First of all, it's going to be visual inspection, looking at things. And just seeing, what does it appear to be inside there? Is there smoke coming out of it? I mean, these are pretty big clues. Is there going to be discoloration? Anything that looks like it's got problems, water in it, that looks like it's been recently disturbed or destroyed or, tampered with or anything like that? All of that's going to go and provide part of our inspection. The rest of it's going to be done with circuit testing, because we can't actually inspect electricity. We can't see it. We have to go and do that through test and instrument measurements, etc. Usually we're going to go and find that either we have lost protection, something has been operated, P&C, as far as our breakers, fuses, overload, switches, etc. That where we have got something that is designed to go and operate that is shutting it off. Or we're going to go and find where we are not making a complete circuit because something has failed. Stuff has burnt open, it's been damaged, we've lost a connection. Or where we have got proper connections and we have got proper components, but it's an actual load problem. So one of those three is what we can expect to go and see. Let's go with inspection of our motor. So we know that the motor is probably bad. The first thing we're going to do is we're going to go and start with inspecting my lines. I'm going to make sure I've got proper voltage at my lines. Once I know I've got proper voltage at the lines, then I'm going to go and inspect and make sure that it's transferring through my switching device, my switch that I have. Once I get through my switching device, then I'm going to go and inspect the fuses. Let's talk about how that is done. The first thing you're going to do is you're going to go and make sure that you're using full proper PPE. You're not working on a live system. You are allowed to test on a live system. You're not allowed to go and work on a live system. So what you would first do is you would go and throw the disconnect. It's not going to make any difference. This motor's not operating anyways. Throw the disconnect so that it is open. You would then open the canister door. And once you've opened the actual shell, then you would go and test across from line to line, line to line, line to line. So you're just going to go and do a test from A to B, then from your B to C, and then back from your A to C. You're going to test to make sure you got proper voltage on each one of these. At that point, what you're going to do is you're going to close the door once again, and then you are going to go and close the switch. Now, you should be familiar with that. On a disconnect, there's going to be a small little interlock on the door. It's a safety that prevents that door from being opened unless you defeat it. They're not designed to be, like some Da Vinci Code level code breaking that you're doing over here, where you're having to puzzle something out. It's usually just a screwdriver that allows us to release that door, so we can release that door with those switches already closed in. You close the switch with the door closed, because the instant that you close in, that's your most likely instant that you would go and have any sort of an arc flash. So you contain that in the can, then you keep the door open. Now you're going to do and defeat the interlock, open that door, and the next thing that you would do is you would go and repeat that same test, A to B, B to C, C to A, but now you're going to be testing on the top side, the line side of your fuses, and just ensure that you've got that proper value of voltage at your fuses. If you've got proper value of voltage at your fuses, then you are going to go and move through to try to test what your load is going to go and have, what your fuses are going to go and have. Ultimately, a fuse is going to go and be an extension of the conductor. Really, it's just going to be a meltable component that's going to be inside of here that extends our conductor through from the top side to the bottom side. So if I'm measuring, line voltage, line to line, and then line to line across the top here, I should be able to measure the same thing across the bottom. However, I'm going to go and utilize a method that's called Crisscross, because Crisscross just works off of one point that we know and off of another point that we don't. Some people will prefer to go and test just going across the bottoms, then going across from line to line like that. There's not that there's anything inherently bad with it. It's just ineffective because if you have two lines that are blown, it's really hard to go and infer any data. So it's much better to, instead of working like this, we work from the top side of one of our fuses so that we're guaranteed that we know at least one of our lines is going to go and be good. Let's take a look at the diagrams that they have showing this. The first one is one that we've already said we've done. This is where we have closed the switch. The switch is upstream from here. They're just no longer showing it. We closed the switch with the door closed, but then we kept the switch in the on position and we defeated the door interlock to get inside of it. First thing we're going to do is we're going to verify that my voltage is good between each of my lines. Line to line, go line to line, line to line, on the tops of the fuses. Once I know that is good, now I know I can go and crisscross to double check any sort of bottoms. All that we're doing is, once again, because this fuse is an extension, I'm keeping one up top here because it's a known good location. And now I'm going to move to the bottom to check if it's a bad location. If I'm measuring full line-to-line voltage, that means that it's being carried through here properly, therefore it's going to be good. If I measure a value that's not line-to-line voltage, 0 volts it could be, but it could also go and be, like 30, 40 or some other weird value of voltage because it's partially feeding back through a load or something like that. Then I'm going to go and understand that I've got a busted fuse off of that one. What I'll do is I'll double check to the next one here as well. I'm checking, that my line C fuse over here. So I checked across. A, I checked across to the bottom of B. B, I would go and check across to the bottom of C. This is if I've checked on my lines. C, I would check across to the bottom of A. That would go and tell me which of these are going to be shot. As soon as I find one that's shot, I'm going to go and test to the next line. That's what we're doing over here. We're moving our tester over onto the B phase to double check that it's not an issue coming in on this side, which is supposed to be our known good side, but rather that it is an issue off of this side that we have just identified. In some cases, you can go and end up with more than one blown fuse that you are going to go and have. This is common, if you end up with a line-to-line short, the fuses are designed to operate really, really quickly, and so they can kick out 2 out of the 3 fuses, sometimes even all 3, although that's a pretty rare fault. This one, we're doing the same thing, going across top to bottom, known good position to a questionable position. And I'm reading 0 volts, so what I would then do is I would go and move this meter lead, take another known good position, and I would just verify. First one tells us, the second one verifies. So I read 0 volts off of both of those, therefore I know that my B fuse is gone. Then I'm going to go and test across from, doesn't matter, you can be testing from the top of B or from the top of A. I'm going to test across to the bottom of C. Okay, that's good to go. Therefore I know that this is a good line, and therefore this one must be good as well because we're getting full line voltage. Move my meter leads, and I'm going to go and crisscross from the top of either B or C, it doesn't matter, but I'm going to measure to the bottom of A, and I see that once again I've got 0 volts, so I would keep this one on here, and I would then go and verify that by checking across to here, and it would once again show me that I've got 0 volts. The crisscross method just tells you that you have got a blown fuse, and it tells you exactly which fuse is going to go and be blown. Because I know that one of them is a good position and the other one is the questionable one. If I was measuring across the bottoms over here, I would get the same 0 volts, but I wouldn't know which one was causing the issue. It would have to involve a bit more testing to sort that out. So check your fuses. Once you know that your fuses are blown, if you've got one blown fuse inside of a system, that can just sometimes be a weak fuse, an overload that went on too long, wasn't caught by the overloads, etc. You can replace that fuse. If you got 2 blown fuses, usually this is going to be indicative of the fact that you've had a massive short on the system, something critical enough that can take out 2 lines simultaneously. Once again, you're going to get new fuses, but don't power it on with those new fuses until you've checked everything else. It's one of the most common rookie mistakes when it comes to replacing fuses is somebody's going to find bad fuses, they're going to take the bad fuses out, they're going to put new fuses in, and they're going to close in on the same fault that originally took out the fuses. And now all of a sudden you've taken out a second set of fuses. So once you verify that your fuses are gone, go downstream and find out what the issue was, first before you go and apply anything properly. Okay, testing everything by measurements. This over here was showing my power that I had. From here, if I knew that I had blown fuses, I would go and test downstream. Excuse me. Let's go back to this one over here. We're going to say these 2 are the blown fuses. What I would do is I would go and test downstream and see what else is going to be screwed. I'm going to, at that point, remove all fuses from the system. I know which are my two bad lines. That now just leaves me an isolated line, and I know that that line should make zero contact with ground here, zero contact with ground here. And so I would just go and test that line to ground. See, with this one, I'd test that one line to ground, this one to ground as well, because that contact is open and the fuse holder is out over here. That switch should be back open as well. That would just mean that I'm going to go and be able to initiate or figure out whether these are short to ground. Then I'm going to do the same thing on the downstream side. The downstream side is going to be trickier though, because if it's this line that is grounded out over here, remember that my motor has got connections inside. It could be a Y, it could be a delta, but it is going to go and have connections. And so I will go and read, going from over here, I'm going to go and read a continuity to ground. And I would read continuity to ground this one, I would read continuity to ground on this one. This just tells me that I've got a ground fault that's going to be inside of there. What I would then need to do is I would need to look at the magnitude. If you've got a good quality ohm meter, your ohm meter should be able to go into the hundredths of ohms. If it goes into the hundreds of ohms, then what you can do, once again, power off because you're working with an ohm meter, take your measurement. If I measure from this line over here to ground and I measure 2.2 ohms, and then I measure from this line to ground, to the same ground that I'm going to go to, and I measure 2.1 ohms, I would know that this one would have to be just a little bit closer for some reason. And then if I would measure on this one and I'm measuring 1.8 ohms to ground, it is going to be the faulted line. The one with the lowest resistance to ground is going to be the one that's going to be closest to fault. So I know I would be then going through this line with a fine-tooth comb, trying to figure out exactly where that fault itself was. It can be difficult to do, pinched lines, shorted lines. Usually what I would do if I measured something like this is then I would go to the motor and I would go and disconnect all of my motor leads just from the motor itself and then re-ohm this out. If that ground fault disappears, off of these lines to ground, then I know that the ground fault has to actually be inside of the motor. There's nothing I can do. That's going to be a motor replacement at that point. If with the motor disconnected and the contacts open, I'm still got a fault to ground, then it's going to be inside of either my overloads or inside of the conductors themselves somewhere. That's my power circuit analysis. Going on into my control circuit analysis, control circuits are going to be analyzed in a lot the same way. We're going to go and work with where we know that we have got power. And I'm just going to go and draw right now two lines that are going to go through here. First of all, you should remember that we don't drop volts until current flows. Across an open switch, we always have got full line voltage. So right now, in a normal switch, I should have line 1 that will extend all the way up to there. Line 2 should go through a normally closed overload. It will pass through here. We won't be dropping any volts across here because we've got no amps, therefore there's no voltage drop. It's an open, and it's going to go all the way up to here. So under a normal, if all my components are good, that's where the whole circuit at this point is open at this point. I press the start. As soon as I press the start, current flow happens. So then we then drop the source voltage over top of this and everything else happens. Most common thing that it's going to be inside of your motor, if the motor's not starting, by the way, before I even pull out my meter, I'm going to just press the overload reset because usually it's just been a momentary overload that's happened and that's been what's kicked the entire thing out. But excuse me, too much talking here. If I press the reset and the contactor, and it doesn't go and start up, the motor won't go and pull in, then I'm going to go through the rest of the testing. Testing is always going to involve me going to my two outside lines, making sure I've got control power. If I have got control power, I know that this overload over here is a normally closed contact. It should be an extension. So I'm just going to move my lead further along here. I should still be reading proper control power. If I'm still reading proper control power, that means that this one is good to go. What I can then do is I can go and move that across, past that one now, down to here. Once I move it across to there, once again, if the circuit is open, no current is flowing, I don't have any voltage drop. V is equal to I times R, right? We have no current through there right now. There's no voltage that's going to be dropped across there, which means that I should have that same line 2 value of voltage that I'm going to go and see over here. I would check that out, the motor contactor, I would check that over here, I would check that over here. And if I check all three of those things, the normally open set of contacts, so your 13, 14 that you have on your contactor, the actual switch contacts, and the actual, this side over here would be my A1, this one would be my A2 of my coil. If I've checked all of those and I've still got proper full 230 volts going across here, then I know that this whole side over here checks out. I've gone through every component along here. Next thing that I'll do is I will go and run through everything starting on the opposite side. Now I'm going to start moving this one. I'm going to move this lead back here to this line where I know it's good for sure. Then I'm going to go move this across here and I'll check. Does that stop button, is that where I'm losing current? If all of a sudden I no longer have that 230 volts, then I know the stop button is faulty. But if I'm still at the 230 volts, I know the stop button is faulty. Then I'll move it across to here and I'm going to go and see if I've still got voltage, see if I've still got voltage over here. As long as I've got voltage off of all these, I've checked the screw terminals to make sure that the wire's actually clamped into the contactor, etc. I'm going to go and be fine off of these ones here. I know that those components are good. The next thing to do would be to do operational checks well energized. So now what I'm going to do is I'm going to go and turn power on. I had power on before, but I'm going to try to enable the motor. When I go and press that start button, I should be able to go and see something that's going to go and happen across it, right? I should go and see that I'm going to have a full voltage that's dropped across it to all of a sudden no voltage. So if I have my meter just into these two terminals here and I press the start button and it goes from 230 volts to 0 volts, that's good. That's what it's supposed to be doing. It's interrupting and remaking that flow of current. So I'm going to go and check it on that actual button. If I'm not getting that 0, if I'm measuring, 10, 20, 30 volts across here, that probably means that I've got bad contact inside of here. So I'm just going to go and check that, pull that thing open, replace the contact block on the back of the switch, etc. Because sometimes it's just a small amount of dust and dirt inside of there that prevents us from generating enough current to go and close in our coils over here. I'm also going to go and listen to what's happening. If when I'm pressing the start button, I'm seeing the voltage change, 230 to 0, 230 to 0, and I'm also hearing the contactor close, but then open, close, but then open, then I would know that it's these contacts over here that are going to be faulty. On some of my NEMA-style contactors, these are going to be done off an auxiliary block that's mounted on top. Check that thing has not vibrated loose or been disconnected or anything, that the physical contact is still tied to the armature that's pulled in, and just meter it up. Disconnect the wires from it, meter that thing out, make sure it's going to be good to go. It's just a systematic working in always from where you know that you have something that is good. Stuff that we do know is going to be good is going to be these two lines, and we're going to just work our way in until that system goes and breaks down. Okay. That's basics of what they had over there. It goes through all the different drawings that they kind of show inside of here. You can go through it a couple times. This is, more the type of thing that you just learn from experience. Let's talk about just the individual types that we have. Reduced voltage starting. If I'm dealing with primary resistance that I'm going to go and have, then I'm going to go through, I've got a bunch of charts over here that I can go and check that are going to tell me specifics about if a motor fails to start, if it starts but fails to reach full speed, if it remains slow too long, transitions to full speed prematurely, overload relay trips, or discolor. Go through these on your own time, up against the book itself. You don't have to do it right now, but later on, go through each of these against that. A, it's going to help you reinforce that theory that you have on how the motor operates, and B, it's going to go and help you understand, why some of this stuff is happening. The motor remains slow too long, the starting speed for too long, incorrect timer settings. What timer would they be talking about? Well, they must be talking about this timer over here, that we're not taking the resistance out soon enough, etc. You got 2 pages of stuff to go through off of that one that are going to be specific. This is very specific to that primary resistance starting. If I'm looking at wound rotor motors with automatic definite time acceleration, this is where I'm going to go and have timers that are going to go and take out my resistances. I'm going to go and have, once again, this whole chart. Why might my motor not be starting? It could be an open in the secondary circuit, so I don't have any current flow. It could be that I don't have any sort of power contacts that aren't closing adequately. 1A, 2A. Go back through these ones here to double check. What they're referring to on each one of these. Once again, this is on you to go and read through and follow. Don't blitz it. I know some of you are just not going to listen to me right now. That's fine. That's your marks. You bleed them. Not me. But actually go through these. Follow these through and work at understanding where each of these goes and breaks down, because your job as an electrician is so much going to be built around troubleshooting. You do installations and then you get called back. If you're not doing an installation, you're doing troubleshooting. It's one or the other. We've also got synchronous motor starters, an automatic synchronous motor starter that's got a polarized field relay over here. These ones have got even more components to go and check and energize, to individually measure values of voltage across. Once again, this is going to just tell you about, hey, if the motor is failing to start, what is it going to go and do? If it's failing to go and synchronize, what is it going to go and do? All of these things are just based upon, that here they have, the motor doesn't synchronize. It could be either an open DC field coil circuit, or it could be that the field contactor is not engaging. And then they go through, how this thing might be not engaging, or how this one might be open off of here. Once again, on you, make sure that you are going through these.